So we found that ideally a bandpass filter has a delay, a phase delay across its bandwidth that is constant. And we know that the phase delay is the derivative of the phase response of that filter. If I take the transfer function h and determine the phase of that complex function with respect to omega, that gives us the phase response, the shift in phase from input to output. I take the derivative of that with respect to omega and multiply by -1. That gives us the delay. And so we might ask ourselves, if we have an ideal filter such that the phase delay is constant across the across the pass band of the filter, what would the resulting phase function be? What is the ideal phase function? So let's look at that. As I just stated, the phase delay through a filter can be determined from its phase response by taking the first derivative with respect to omega and multiplying by -1. For an ideal filter, this delay would be a constant for all frequencies. And so from this, we can find the phase response by solving this differential equation. What is this function, the phase, the argument of h as a function of frequency? What phase function would satisfy this equation? Now you may be happy or perhaps a little saddened to find that this is a very simple differential equation and one that's easily solved by integrating each side of the equality. When we do that, we find that we get a phase response, a phase function with respect to omega, which is equal to this, simply a minus omega times that constant tau. And of course, this harkens back to an example that we started off with when we talked about filters and phase responses. The filter is ideally one that simply delays any signal at its input by some specific value, reproduces it precisely, only shifted by some value we'll call tau sub c. So then if we were to plot the phase of this ideal transfer function with respect to phase, we would find we get this sort of sawtooth function that we looked at again earlier in an example. Remember, these transitions are not physical per se. They are simply an artifact of the 2 pi modulo, that once the phase drops all the way down to -pi, we jump up and start again at pi, essentially rotating around the unit circle. We get to one side, we start all over again. This slope of the phase, though, with respect to omega, of course, is constant. Each part looks like a line. And so we call this phase response the linear phase. And such a filter with this linear phase response, we call it a linear phase filter. And so we talk about a linear phase filter being ideal. And the reason it's ideal is because of the phase delay that results from it, a phase delay which is a constant across the bandwidth of the filter. Now, having said all this, this ideal characteristic is one that is seldom found in a filter, one that's difficult to build, and more precisely, as we'll see in a little bit, if we build a filter with an ideal phase response, we pretty much have to sacrifice every other artifact of the filter that is desirable to us. Specifically, if we come up with a phase delay function, which is ideal and perfect, our power transmission function, the function that defines the bandwidth of our filter and the roll-off and such, will be typically insufficient for most filter applications. However, the idea of linear phase is something that is desirable, and the closer we get to this ideal condition of a linear phase filter, the happier we are, because again, the less we have to worry about distortion of our signal due to dispersion as it propagates through that filter.